everyone. So we are so gonna, so we're gonna mostly finish our session on linear regression. Okay, let me pause this. Okay, great. So yeah, so we're going to kind of finish kind of the core section on linear regression, but we're going to actually come back to this. The next section will be on gradient descent, and we'll talk about gradient descent in general, and then we'll see how to apply this onto the regression problems we've been looking at as well. So but if we first just look at the schedule, so today there's not going to be any so there's not going to be any core new material today. So I'm going to the goal of the lecture is to review some things that I think we went over slightly fast when we went over them during the core lectures. So I'll probably spend about 15-20 minutes doing like a recap of the stuff we covered in this section, and then after that I'll kind of open the discussion up to questions. If you want to ask me any questions for further clarifications on something, or I can go into a little bit more depth on one of a few topics. I was thinking of either the proof of why that we have this kind of basically closed form solution for linear regression, why this is true. I can work that out. I can talk a little bit about kernel regression, another extension that I don't know if it appears later in the curriculum very much. So those are other things I can do. I can also just answer questions because because quiz number 3 is today. And so if you have questions on what might be on quiz number 3, we can go over that. So yeah, so question is, overfitting cross-validation going to be on the quiz? Yes, overfitting cross-validation is going to be on the quiz. It's going to be these kind of 3 lectures. It's probably zoomed in too far. So let's see if I can do a highlight. These kind of 4 lectures here. So from the last lecture, my highlight went missing. Okay, so from the last lecture on inverse and orthogonality, I'm not going to ask you to actually take an inverse, right? But the last lecture on linear algebra review, because that one was the day of the last quiz, so it covered potentially on this quiz. And then the 3 lectures so far on linear regression, including overfitting and cross-validation. Yeah, so will we be revoting on the cheat sheet? So sure, yeah. So it's the cheat sheet. Yeah. So I forgot to do this earlier. The cheat sheet is built into this quiz. We're not going to change it because we'd have to do it in the next hour, which is during the lecture. But so we could vote on the 2 options. The 2 options, I'll type these into the chat. So one is as is, 5 points, 5. So 5 bonus points, not exceeding 100%. Option 2 is 10 points. So these would be counting towards the total of so 100. So these are not bonus, right? So these are the 2 options on the cheat sheet. Again, so I'll be asking to turn this in either way. In the first option, if you don't do it, you're not losing any points, and you can get 5 points, and those are added onto your score, which is already out of 100 points. This is what we have been doing, but you won't exceed 100 points, right? The second option is there'll be 90 other points on the test, and you will get to, and plus these 10 points for the cheat sheet, the total grade will be out of 100, right? So you're basically required to do this. So the cheat sheet is graded in the sense that it has to be there and it has to be on topic. I'm not going to enforce what you put on the actual cheat sheet. I'm pretty flexible about that. I think it works best if you write it out by hand or on a computer and you take the time to do it as a good study guide. But I'm not but either case, it's going to be built into the requirement for the quiz, right? Just like it was on quiz number 2, and the scores are better. Yeah. So, okay. So let's do a vote. So we're going to do 1 equals yes and 2 equals no. Okay, so everyone, you can click the green or the red button inside of the participants window, and it only allows everyone to vote once, and I can see a counter. So 1 is yes and no is 2, and those are going to be the 2 options. Okay, it's a close race, so make sure you vote. Only about, let's see, there are, yeah, only about half you have voted so far. You know, in general, I encourage everyone to vote if you're legally allowed to vote. So someone asks, what are we saying yes or no to? Yes and no are just the 2 easiest to use buttons that I can use for voting. Yes is option 1, which is the current, what we did on quiz number 2. You get 5 points added to your score, not to exceed 100. No is option 2. You get 10 points. That's the total part out of 100, but it's not a bonus point. Yeah. So it's not a poll. It's in the participants window. Yeah. Yep. So there's no voter suppression going on here. At least I hope not. If you didn't show up for class, maybe, but yeah. Great. We're getting close to 100% voting. There are about 5 or 6 or 7 of you who have not voted yet, and then the people who aren't here aren't voting. Hopefully, that's not a form of voter suppression. But it looks like option 1 is winning. It's a slight lead, and because that was the choice, so is there a vote by mail? So yeah, yeah. So I think this will be fine. It seems like it's pretty close, anyways. And so I ultimately decide I could probably put my hand on the scale a little bit here. Not going to get too close to commenting on the actual political situation, but so I think we're going to stick with option 1 here, which is the status quo. So it'll be, I think this is the option that you get actually more points. You still get a chance to get all 100 points, and then you can get an extra 5 points on top of those to make up anything you lost. I think this is the better option for you. So I will stick with option 1. So yes, okay. So I'm closing the voting. So that's that. So, okay. So great. So thank you all for voting in this. So just to be clear, it will be option number 1 above as in quiz number 2, and we'll stick with this for the rest of the semester. Okay. Okay. So the next, the cheat sheets are turn in one side of one PDF. Okay, that's the intention. The intention is you should be able to distill it down to one sheet of information. It's, you can use your notes and the book and stuff on the test, but I want you to have one cheat sheet. Okay. That's one side of one PDF. That's what you will turn in. Okay, I think that's the right amount of material for these sorts of things. If you're writing a lot more material, you know, it's probably going well beyond kind of the core material, which is great if you're writing that down in your notes, but I want you trying to think about distilling it to one page. So great. So the next thing is I slightly changed the schedule of the class. I was kind of, I was given the heads up that, you know, the university said something about not having any synchronous stuff on the day of the election. And then I heard, I don't know if this was official, that they didn't want it the day after the election either. And those kind of hinted, well, we didn't have a fall break this year. And I know it's kind of, it's getting to the point of the semester where you can really use, you could really use a break. So we're going to kind of do it around the election day. Guessing for a lot of you, there's probably going to be a lot of other thoughts going on in your head around those days. So that's probably a good time. The goal is not to have you guys all travel and have some pool parties or something like that, but to just kind of have a mental break from what's going on in the semester. And so we're going to not have class on November 4th, which is the day after the election. So, okay, yeah, so I think it sounds like a good idea. As well, I had scheduled, so I shifted all the lectures back one day. There was the last lecture, the last scheduled lecture was the plan to be an in-class review. I've done the last few semesters in this class and students seem to like that. What I'll plan to do is I'll find it, I can still do that. I'll do another time to do it, but it'll be outside the class time. You know, our exam is pretty late this semester, where I think we're one of the last exam days. We're like December 11th. So I should be able to find another time. Tentatively, I'll do it Monday on the Monday during class time, the day after the semester ends, our regular time. And I'll post something about it as we get closer. But I want to make sure it's not like during another big exam or something like that. And it's too hard for me to try and figure that out. So I'll post something there. And so we can still do that. And if that particular time doesn't work for a few of you, we can maybe schedule something with maybe the TAs can do something similar. And the past, I've basically just gone through this practice exam linked right here, which is a bunch of questions, way more than what will be on the final exam. And I've just gone through and answered all of those questions. There are like 16 questions. And the final will probably have like 8 or something like that. But so that's what I've done in the past, but I can answer any other questions as well. Okay, so I want to, I realized that I did not move the quizzes or the homeworks either. I like kind of, the homeworks are every 3 weeks on a Wednesday, and the quizzes are due every 2 weeks on a, and they're always on a Monday. I kind of like that. I don't want to move the homeworks. I think that would shift things kind of too much. The last homework 5's already due kind of after the last day of class. But I realized I could shift the quizzes. And because we don't have a quiz 7, which would otherwise kind of be on the day after the next potential time after a lecture. So I could shift all the quizzes by quiz 5 and 6 by week. I'd be open to doing this. This would allow us to actually quiz on most of the classification section, which would allow you to prep for the exam a little bit on that. So does that seem like a good idea? So let's do a poll on this as well. So it's going to have yes equals shift quiz number 5 and number 6 back 1 week, and no equals status quo. Wow. So quo, if I spelled that correct, or not, that looks French or something, I'm not sure. But so you can vote yes or no again. Okay, Okay, again, pretty even split. We must be one of those swing classes. Okay, we have. Oh, people are changing their votes. If you click more than once, if you try and vote twice, it undoes your vote, and I won't send you to prison or anything like that. Okay, so okay, it's pretty split. Okay, so I'll probably think about this. The yeses have a slight advantage, which would be shifting it back by so quizzes 5 and 6 by a week. That would give you a little bit more of a real break then, because kind of the quiz is also pushed back. But then you would have a quiz a little bit later in the semester, at the very end of the semester, which is probably going to be hectic as well. So okay, so I'm gonna would increase the amount covered on quiz 5. Yeah, so I would then, so there's this last lecture on dimensional reduction, which as currently planned with the shift back, I would not cover that on quiz 5, which is probably okay. If there's anything really important, I can try and throw it in an earlier lecture to make sure it's covered. So I would make sure I would cover that one extra lecture in quiz 5, which I would prefer. That makes it a little bit better that way. And then quiz 6, I'd be able to ask about the first 2 sections of classification. Vote again with, so someone wants me to go slower, go faster. So these votes are pretty even. So it seems like, you know, some of you have strong, if you have strong preferences, those are kind of split. There's a little bit hesitant, you know, desire to move it back. I'll probably talk with Hassan after class, and so we'll probably decide what to do. But I'm leaning towards moving back quiz 5 and 6. I think this would work a little bit better. So great. So okay. So good. And then okay, last thing, homework 3 is now officially posted. Let's see. So the first part of homework 3 is going to be on regression. And then yeah, the first 2 parts are going to be on regression. The first question 1 is going to ask you to actually perform regression, and go to the collab files we did in class as a starting point of doing this. I recommend you do that. That'll make your life easier. For part D, I want you to actually work out the expansion. And if you use the built-in function, I showed that, you know, you might be able to extract it from there, but you have to figure out to make sure it's doing the right thing. So I'd recommend you try and do part D by hand. It's not very hard, or I hope it's not very hard. But so start with the collab files I give you, and that hopefully will make this not so easier. But this is the first like kind of substantial programming part of the class. Look, I think you're all computer science majors or close to that, and so I don't think this is a big programming assignment, but you'll be doing this in Python to see how it works. Yeah, so you can always do basically everything you want in Python and Collab on these homeworks. You know, I want you to answer the questions, and sometimes it's required to write some code to answer it. Okay, I mean, like back in the day, I think Gauss did linear regression by hand a long time ago. So it's you know, before, you know, this was at like the 1800s when Gauss was around, 1700s. I don't know, but I'm not expecting you to do that. Yeah, so go ahead and do it in Python. Question 2, does not need Python. Question 2 is more of an analysis question. You don't need Python to do. I don't give you any data to work with. But question 3, again, I'm giving you these functions, and I want you to do those again in Python. That's going to be based on gradient descent, which we're going to cover starting on Wednesday. And again, there's going to be some collab code that I'm going to present to you and go through. And if you start from that collab code, the only part you should really be working on is the part I want you to spend time thinking about, kind of not actually writing all the infrastructure. Take that from the collab file again. You don't have to use collab. You can do it any Python you want. If you really want to do it in a different language, that's probably fine, but we won't be expected to read or check your code, but you need to kind of make sure it outputs the right sort of answers. But I've given you a lot of infrastructure in Python to make it easy for you. Okay. Okay, so take a look at that. There's still kind of plenty of more than 2 weeks to work on that. So you can get started. Yeah. So that's where we are. Okay, so let's get into this review. So again, I'm going to do about 15, 20 minutes, so about 2:05. I think I'm just kind of review some kind of the core part of regression, the most important part, hint, hint, and then you can ask me some more questions on that. Okay. So this is a supervised learning problem. Okay, so that means this supervised part. Okay, that means that the input comes of the data comes in the input with 2 parts, X and Y, where this Y are these labels. Okay, and so in general, X is going to be a subset of R n times D. That means it's n data points in D dimensions, and Y is going to be in R n. That means these are going to be n values, the vector of these n values. Okay, and so the goal, the goal is to build a linear model to predict Y, or actually on new data that looks like Y, or like X and Y. Okay, so and this linear model looks as follows. It gives you a Y hat. This is the prediction. It's a model M alpha. It takes in a value X. This is a value here. This X is in RD. This is a D-dimensional input, and it's going to be alpha 0 plus alpha 1. So this X equals X1, X2, up to XD. X1 plus alpha 2, X2, up to alpha D XD. Okay, and so we can think of this model is parameterized by this alpha vector, which are these parts here. The x's are is going to be the input data, right? So the data, when we evaluate a new data point. We plug in the value x, which are these explanatory variables, and we're going to, take effectively the dot product with this model, and we're going to get this prediction. And the goal is to find, find alpha 0 up to alpha d to minimize the sum of squared errors x, y, alpha, which is going to be the sum equals 1 to n of all of the data points of this model m of alpha xi minus, so this gives me the value which is predicted, minus the yi value I observed. I square each of these, and then I'm summing all these up, the sum of squared errors. Okay. So x is, so x a subset of R and R cross D, not times D, cross D. So there's a question about this notation up here. If you remember, this means x is going to be a matrix. This n cross D, right where I do this, that tells me the dimensions of a matrix. So just to be clear, x looks like this, where I'm going to have n rows and d columns. Okay, each of the data points, right, each of the actual data points, this is going to be xi, which is in Rd, but I'm going to have n of these, and I stack them in a matrix. Yeah, okay, great, you're right. That is an element of, you're right, thank you. It's a subset of Rd, or yeah, there's great. So it's in Rd, so it's an element of this n by d matrix. Great. Yeah, great. So y hat, yeah, so when I discuss this, when I write y hat, this hat notation this guy indicates it's some form of an estimate. If I put a hat on, I'm estimating something. Okay, so if you see someone with the pointy hat, they're an estimation. I can use different models. We'll see later in classes, and we'll get some estimate. And if I put a star on it, that's usually the exact answer. So this is just notation as common here. So you could do an estimate which is not from linear regression. I might still use the y hat here in this case. So, okay, great. So this is the goal. And the goal is specifically to estimate error in this labeled coordinate, right? So I'm trying to predict this label. And so I measure the error in the vertical distance. If I were to plot this, I measure it only in this y coordinate, which I'm trying to predict here. Okay. The general solution, the solution to this is we'll go through in two steps. First, we'll map x to x so tilde, okay? And so this will be in an element of n times d plus 1, okay? And so if we have a matrix X, which is is n by d, then we're going to add a bunch of all ones along here, all ones in this first vector, okay? And then we're going to get this matrix X so tilde instead, where we're going to add these ones matrix in front. So xi tilde, squiggle, okay, the tilde on top is going to be 1 times xi, right? So this is an element of R d plus 1, Okay, so we're going to do this, and now we can basically pretend that there's no offset coefficient, but that there's a first kind of vector of all ones, which kind of serves to describe the offset. Okay, and so often, and I think for the rest of the class, we'll often remove this tilde notation. We often won't use it. We may just assume it. So we can often write the goal of is to find the alpha star equals the arg min of x tilde alpha over alpha in rd plus 1 minus y. So I can write it now, this formulation is in this kind of this linear algebra notation. Basically, it's an L2 norm or L2 norm squared, this same minimum of x times alpha. So I'm dotting every row of x tilde with alpha. I'm doing a dot product, and I'm comparing, and that gives me a scalar value, and I'm comparing that to the y value that I have, this equivalent statement, right? And this, but often you'll see this expression, linear regression is just this without the tilde. People ignore the offset because you can add that in or assume that that was part of the input data. Okay, so sometimes this tilde thing is dropped, and you should keep in mind if I actually have that all ones vector, then I'm allowed to have an offset. If I don't, then I don't have an offset. I might force my model has to predict a value 0 when x is the all zeros vector. Okay. Okay, now we can say there's a solution. So the step 2, solution step number 2 is that I'm just going to set alpha equals to, and I'll write this out explicitly with tilde, x tilde transpose x tilde. I take this as an inverse x tilde transpose times y. Okay, so this linear algebraic expression gives me the optimal solution for alpha, which minimizes the sum of squared errors, or this kind of this linear algebraic way of writing it. I just wrote down here in the red as the goal. Okay, so once I've added this all ones column, I have this simple linear algebraic solution. Okay, and I might ask the same question, but like sometimes you drop the tilde because it might be implied, just so the notation doesn't get too messy. Probably when I did this before, I forgot to add some of the tildes, or they don't look right or something. So they're often dropped for that reason. Okay, so this is how you build this linear model with least squares regression. There's basically a closed form thing. They call these operations within, inside of Python or any library or programming language that can do linear algebra, and I output the optimal solution. As we'll see, the inverse is not quite a closed form thing. There's actually some secret iteration going on, and we'll see how to solve that in a few weeks. When you say tilde is dropped, you mean that we will just use x, or that alpha equals y. Yeah, so when I mean tilde is dropped, it will often be so written as the goal is just arg min alpha x alpha minus y squared, and the solution is just going to be alpha equals x transpose x inverse x transpose y. Okay, so often we'll just write it this way without without the tilde on the x, because it's kind of a cumbersome notation. And okay, so the way I've stated here in green, the solution is forced to go through the origin, which means if you put in all zeros vector, it has to predict that the y value is 0, which might not be true, might not be a good model. But I could have assumed that before I did this, before I created my X, I added an L1's column at the beginning. So that was kind of built into there. And I think the one on the homework I give you has this built in. So you don't need to worry about this step. And so this is often the way it's discussed. So it kind of simplifies this discussion, but it's important to understand this distinction. Okay, so yeah. So this is part of the place where the literature on this can be confusing, because if you look up 2 articles or 2 papers on this, one of them will discuss having the offset and one won't, or they will discuss it sometimes having the offset and sometimes ignore it in the formulation just because they're being sloppy. I'm just kind of letting you know, it's kind of intuitively you should know what's going on here. And sometimes people forget to mention about the offset, but this is how you deal with it. Yeah, so it's not hard to do, but kind of it's a small distinction which sometimes makes a difference. So okay, so this was linear regression. I wanted to quickly say about polynomial regression. Okay, again, this is now, we'll only talk about this when we have as input xy, where x is in Rn and y is in Rn. This generalizes to when x is d-dimensional variables. It's just kind of messier. We'll mention how to do this expansion a little bit later. Maybe I'll do it after I finish the most important review. But so then what this says is that the model y hat here is going to be m alpha, and we'll say to some power p, right? So this is going to be the power of the polynomial here involved of some value x is going to look like alpha 0. Again, the offset built in here, alpha 1, x. It's just a scalar now, right? So now this x in this case is in R1. So it's just a scalar value, just for, as we'll worry about in this at this point in this class. But then it gets interesting. Alpha 2 is another coefficient, and you do x to the power 2 up to eventually you add alpha p x to the power p. Okay, and you can rewrite this in a compact complete form as the sum j equals 0 up to p of alpha 0 x to the power, say, alpha j x to the power j. Okay, and remember, when I take x to the power 0, it becomes a 1. When I take it to the power 1, it doesn't do anything. When I take it squared, and so forth. So this is just a compact way of writing this model, right? So it looks pretty similar to a linear model with a lot of variables, except I'm just taking that variable to the jth power from every power from 0 up to p, right? And then if we're doing this with multiple variables, I need to consider all pairs of variables up to the power p. Okay, so let me finish the core review, and then I can maybe say a little bit about that. I'll just go through a slightly more complex example. So, okay, and then the solution to this is again going to be fairly simple. So the solution is going to have 2 parts again. One is I'm going to construct this x tilde, which is now going to be an r n times p plus 1 instead of d plus 1 for this power, where x tilde equals to, so this is the first, well, the first coordinate is 1, the second coordinate is x1, third coordinate is the first row corresponds with the first data point, which is of a value 1, right? But now it's squared. up to x1 to the power p. This second row is x2 squared, x2 to the power p, and then all the way down to xn squared, xn to the power p. Oh, and this is, we'll call this x tilde to the power p. Okay, this is, let's do sub p. I think that's what I did. All right, so sub p here, okay. And so again, I just constructed this kind of expanded matrix, kind of like I added this coefficient 1 in front, but I added all these powers. And then again, step 2 is pretty simple. I just do alpha star, the version p, which is x sub p tilde transpose x sub p tilde inverse x sub p tilde transpose y. Okay, so the solution is basically as simple as before. I just have to do this expansion first into this matrix, so I add more columns, and this allows me to then kind of build this polynomial model, which is again just these coefficients here, but now they're coefficients of these polynomial powers of the input data. Okay, and after I expand this matrix, basically it's very similar than before. I get the same sort of results as before, and yeah, so it's again basically a closed form solution. Okay, and as we'll see in a week or two, that with gradient descent, you're also going to get a pretty straightforward way of getting a solution for this. Basically, a very, very similar trick here. So, okay, basically I want to cover, let me just say, yeah, so I think I didn't go too fast on cross-validation. So just to kind of say a couple words on cross-validation, because this is very important. So first, this is specific for linear regression and the other forms of regression is that so I have to define, this first thing is specific for just linear regression, but I have to define the residuals. Okay, and so my error is going to be, in general, is going to be the sum of these residuals squared, where the residuals I is going to be the model xi minus yi. Okay, so I'm measuring specifically in this y coordinate, right? So I'm getting some model through here. If I have a data point, then I'm measuring, this is the data, this is the error here. Okay, so this is, now with cross-validation, I can do this with any supervised problem. I might measure the error in a way which is different than this, but this is the case for regression. Okay, and now for cross-validation, I'm going to split data x and y into x train, y train, and x test and y test. Okay, so I'm splitting the data. I'm pulling out the rows and the label and splitting this into training and testing. And then I'm going to build model alpha on x train, y train, and then I'm going to evaluate alpha on X test and Y test. Okay? So it doesn't matter if you subtract Y hat from YI instead of subtracting YI from Y hat. The book has it both ways, which is which is confusing. So yeah. So here I have this residual as the model minus the observed data. Yeah, so it flips the sign if I were to write this down instead as yi minus y hat xi. So in some places you can say the residual is the absolute value of those. We're typically going to talk about it with an sum of squared errors, or at least something that looks like an LP error. And that's going to involve, the norm of it's going to involve the absolute value here when I discuss the norm. So in that way, it doesn't matter. I think it's useful to have a sign there because the expected residual should be 0, kind of if you have an unbiased estimator. Okay. And that way, it doesn't matter which way the sign is, as long as if the expected error is 0, if I multiply everything by -1, the expected error is still 0. Okay, because of linearity of expectation. So it doesn't really matter which way I do it. I think it's worthwhile to keep some sign around so that the expected value is 0. The squared expected difference from the model, right, or the average of them would be like the variance, and that tells you something that's not expected value 0. That tells you the expected variation, right? But so that's why I think it's useful to have a sign, but it can lead to this confusion. And I apologize if I swap them around, but it turns out it doesn't matter so much as long as you're self-consistent. Yeah, I guess I wasn't self-consistent, and I should check that out. So thank you. Sure. So okay. So let's go back to cross-validation. It's important that you build on alpha and then you evaluate. You build on the training and you evaluate on the test. And this allows you to ensure that you're not overfitting by testing on the same data that you evaluated on, or to testing the same data that you built the model on. Otherwise, you can interpolate stuff and it looks like the error is 0, but on new data, right, it's not going to be so. And so this is basically an approximation of the new data not yet so seen. Okay, so this is, we want to do well on data we haven't seen yet, but because we haven't seen it, let's do it on the data we have, but let's pretend we haven't seen it when we build the model, right? So we exclude it from the training part so that, you know, we separate the test and the train so that, you know, we don't spoil the model with what we're using to do the evaluation on. Okay, so if you have a line above yi, it would have the same variance as a line with yi above and below it, assuming, yeah, so right, so if I write down, I'll come back to, here, let me say just one more thing about cross-validation. You can use cross-validation, and then I'll answer that question. So you can use cross-validation to evaluate alpha to do one of two things, to either choose a model or to predict something like the variance of the estimator. But you should use it to both simultaneously, because if you use it to choose the model by like a parameter of the model, then that's part of the learning process. And again, you don't want to use that same thing to try and predict the variance. So not both. Okay, great. So okay, so if we have, so the question, this is a useful question. Let's say we have some model M alpha. Okay, and we have some some data points. Okay, and let's look at one of these data points. This point, this is the x value, and you could think of this as being our d. There's d dimensions down there. Think of it, it could actually, be other dimensions down there. I can't see, but okay. So, or you can think of it as one dimension. That's fine. And then this is the y coordinate. Okay, and so now if this guy, the coordinate here is x1 or xi, yi. Okay, in this case, this would be the residual, and it's a vector from, so this would be yi hat by the model. This is m alpha of xi, right? So that's the value I get, that y coordinate. In fact, it's the y coordinate. Okay, so that's the value I get, and I'm predicting right there. And so this residual is the difference in y coordinates here. So Ri, in this case, yeah, so let's do it this way, m alpha xi minus yi. So yi hat minus yi. Okay, and so the question is, if the same variance, yeah, so if I look at all of these and I were to swap it, right? So now it's a vector pointing basically down from the model, so onto the data. And there's a nice interpretation of it this way, that I'm building the model, and then there's some orthogonal kind of term that's coming off this, some of the n-dimensional space defined by the model. There's some orthogonal term coming off pointing onto the data. It's orthogonal from the subspace of the model in n dimensions. This is more of a d or d plus 1 dimensional plot. But then I can basically say that yi is equal to yi hat plus this residual. So the true value is the model plus what's left over, which is this residual. So okay, so if I were to redo these, right, and if you notice these are kind of balanced as I chose this, and I were to take, if this was R2, let's say this is R1, R3, and R4, right? Now the variance, it's a sample variance on here, right? But okay, so the variance is going to be the expected value of the difference between the yi's I see minus the expected value of them, and the expected value of them in this case is represented by this model. Okay, and I'm squaring this. So this kind of represents the expected value of the yi. And that's why, given there's some, to do this right, you can do a full kind of Bayesian kind of or statistical kind of derivation of this, given the value xi and the data. Okay, so if I look at the variance, it's the expected value over the choice of I, but it's basically an average, which is the sum of the differences squared. But when I square it, right, I'm taking this term which has a sign, but then I'm squaring it, so the sign goes away, right? So that's why it doesn't matter so much which way I put the sign. So it's nice that the expected value, if I didn't do the squared difference, the expected value should be 0, right? And that's only there if you carry the sign. Okay. Hopefully that tangent didn't add confusion onto this, but if there's still confusion about the residuals, please ask. Sure. So okay. So there's so we went into a bit more stuff than the short review I'd planned. We have 10 minutes left until the quiz. Happy to answer any questions, or I could try and quickly go through. Do we have time to talk about eigenvectors? Sure, I could talk about eigenvectors. We're going to talk more about them later in the context of the SVD and dimensional reduction. But we could talk about those. We could also talk about the proof of why this solution step for alpha is correct. Or we could talk about, maybe you could talk about kernel regression, which is another form of regression. If no one else says anything, I'm happy to talk a bit about eigenvectors. So sure. Okay. So let me talk about eigenvectors. Okay. So eigenvectors are they're defined with respect to a square, so matrix M. So we'll say this is in n by n. Okay, good. N by n. Okay, so we have an n by n matrix. Okay, and to avoid some complications in this course, we're going to assume, so in this course, these eigenvectors, these square matrices we're going to talk about are always going to be derived from data. Okay, there are places outside this course where they come up in other situations. In this course, they're going to be derived by data, and the data does not necessarily give you a square matrix. So what you start with, you often start with this kind of this so data matrix, and we'll call this A, which is going to be in R n by d. Okay, so this is the data matrix with n data points and d attributes in some way, and they don't need to be, n does not need to equal d. And then we're going to do m is equal to A times A transpose. You could also do A transpose A, but that gives you a d by d, and we had n by n here, okay? And so basically every time we talk about eigenvectors in this course, we're going to derive it from data in this way. Okay, so this gives rise to special structure. This ensures that M is positive, so is going to be positive semi-definite. Okay, this is kind of a nice property to have. This one way of seeing what this means ensures for any x in Rn that x times m times x transpose, this value is going to be greater or equal than 0. It might be equal to 0, might be greater or equal than 0. Okay, so we're going to assume that our square matrix, we're now going to assume that our matrix is square and that it's going to be satisfy these two properties, square and positive semi-definite. This gives rise to another property that's related to eigenvectors for a square positive, this is often abbreviated, positive semi-definite. So matrix M in R n by n, then it has all real and non-negative So eigenvalues. Okay, so well, I haven't said in this kind of burst what eigenvalues are, okay, but it's going to ensure that they're all real and that they're non-negative. That means they could be 0 or they could be positive, but they can't be some sort of negative number. Okay, so if you deal with general square matrices, you might get all sorts of weird eigenvectors and eigenvalues. They might not be real. They might have complex components. They might be negative. And this kind of really warps the intuition about what's going on, I think, which can be really nice otherwise. And so we're going to avoid all that weird stuff. And you might have a linear algebra class that focuses 2 lectures on these other cases. And those only come up by accident, you know, or if you did something wrong, usually in most data analysis. It's not entirely true. You can get into these kind of specialized areas where they deal with them. But for most cases, we're going to be able to assume this about the matrix. OK, so now the eigenvector and value structure, given this M, is a vector V such that if I multiply it by the matrix M, I'm going to get back lambda V. So what's going on here is this V is, so this is going to be a V in Rn is an eigenvector. And when I multiplied it by the matrix, I'm getting back a scaled multiple. So this is now a scalar. So now lambda is a scalar value. It's an Rn. And in fact, in this case, I know lambda is, so it's real. I can say it's real because I have positive semi-different matrices. And I also know it's greater or equal than 0 because they're positive and so semi-definite. And this is called the eigenvalue. Okay, so eigenvectors and value give me this special structure. Okay, and so if I have a matrix M that is n by n, I can get n orthogonal and distinct eigenvector. So eigenvectors. Each one corresponds with an eigenvalue. Okay, right, and we typically present the eigenvector so it's a unit vector. Okay, so often presented as a unit vector. The scaling doesn't matter because if I scaled both sides by 2 of the equation up there, if I scaled both sides by 2 here, it can be pushed into the eigenvector. So I can take out the scale, and usually I make sure that it's L2 normalized. So it's L2 normalized 1. Sometimes I make it L1 normalized. In the data mining class, when I deal with kind of Markov chains and PageRank and stuff like that, you want to L1 normalize it. But okay, so there are n orthogonal eigenvectors. That means that eigenvectors v1, v2, so satisfy that v1 dot v2 is equal to 0. And you kind of think of that as, so v1, v2 are going to be orthogonal. That means there's going to be a right angle between them. Can there be 2 eigenvectors to 1 eigenvalue? So yeah. So there's non-uniqueness on the eigenvalue, and this leads to, I was able to get rid of a lot of pain by assuming that we're positive, so definite matrix M, but I can't assume this away. Sometimes this happens, and this leads to some kind of, you have to be a little bit careful with things, but generally it works out. If this is an issue, you're often looking at something which is a property which is not stable. Yeah, so you can have multiple eigenvectors with the same eigenvalue, but typically you're sorting them and the top eigenvector has the largest eigenvalue. Yes, okay. So, and the most value captures the most variance, right? I'll say one more thing and then I'll end so we can do the quiz. So the largest eigenvalue, often called lambda1, corresponds with eigenvector v1 in the direction of most variance in A. In the original matrix, we multiply it by itself to get M. Okay. Yeah, so we'll talk about this much more, and this seems like a really cool property to have, the direction of most variance in high-dimensional data, and that's going to be useful in dimensionality reduction. All these same properties, basically, they're very related, corresponds with the singular value decomposition, which is doing basically the same thing, but on these rectangular matrices instead of the square matrices. And so we're going to focus on the singular value decomposition interpretation, and then we're going to see that the singular values correspond with eigenvalues, or the singular values squared correspond with eigenvalues, and the singular vectors end up being eigenvectors in some ways, but we'll kind of reapproach this. And so if this is kind of some pretty wild ideas and you haven't seen these ideas before or some aspects of them, this would be all kind of useful to know now. And we'll spend 1 or 2 lectures kind of unraveling this and thinking about this from the perspective of the singular value decomposition instead of the eigenvalue decomposition, which is what this corresponds to. So great. So I'm going to kind of stop the core of the lecture now, and the quiz is now open. Although I'm going to be around here to answer questions on the quiz, or if you want me to talk about something else, it's my office hours. Oh yeah, do we need any collab knowledge for the quiz? No, you don't. I guess I don't want you using collab on the quiz. You probably could, but it's kind of starting to search the internet, which is what I don't want you to do. You should not need collab. I will not ask you anything that requires doing anything near that complex of a computation. So please don't use collab on the quiz. Okay, you can use things linked off the web page or your own notes, but I want you to distill 1-page notes that you will upload, and that will give you up to 5 bonus points, not to exceed 100. The page where you explain variance. Okay. Yeah, so it's kind of variance. There's a way to define the sum of the squared errors as variance with regression more formally. That requires a longer treatment, which is kind of most of a semester of a 6,000 level math course here. I don't think it needs the whole semester to do that, but that's kind of the focus of, I think, Math 6010 is really diving into this. And this is just kind of some intuition of what's going on. But whenever you see sum of squared errors and the error is measured from something that's kind of like the expected value, then that's basically something like variance is a very reasonable way to think about it. And there's usually some way you can derive some model where it is the true variance, but to derive it takes some work. Okay, I'm going to stop the YouTube streaming.